Hey there, physics students. All my favorite juniors and seniors, nice to see you. It's been a while since we last spoke this way. I am here on Friday, May 15th, ready to give the seniors their last video lesson. This one is on series and parallel circuits with Ohm's law. So with the help of Jarvis here in a minute, I'm going to switch over to just the document camera and we're going to work out a couple of examples. When you're finished, make sure you click on the worksheet that I provided in Classroom and see if you can't work through those problems. I hope everybody's doing well. I miss all you guys dearly, and I really wish that we didn't have to end the year like this. So Jarvis can give me a hand here and switch me to just my document cam, and I can see better. Okay, there we are. We are looking at, if you have your books and you want to look at the problem, you can. But as you can see, it is on page 471. I wrote it out. It's number 2. And the problem says a 10 ohm resistor, a 15 ohm resistor, and a 5 ohm resistor are connected in series across a 90 volt battery. And the first thing we have to consider is what's known as equivalent resistance or total resistance. And when you're working in series circuits, since everything is in one line and there's only one path, this is nothing more than adding the resistors together. So this is 10 ohms plus 15 ohms plus 5 ohms. And then the total resistance for this circuit, the series circuit, would be 30 ohms. Okay, so that's pretty straightforward. Then for current here, it says to calculate the current, and of course we're using Ohm's law that says V equals I times R. So if we're solving for current, this becomes current equals voltage over resistance, and the voltage in the problem is 90 volts, and the total resistance we just calculated is 30 ohms. And when we divide 90 by 30, we get 3.0. And remember, current is measured in a unit known as amps. Okay, so you know, the application of Ohm's law in a series circuit is pretty straightforward. Really no different than the Ohm's law practice problems we did. But now we're going to look at a different scenario here where it shows the same circuit, the same devices, but now we're going to set it up in a parallel circuit. So the problem we have with this, and I don't know if you guys noticed when you were doing your circuits lab, the virtual lab, if you didn't notice that the lights were brighter in parallel. And that's because what actually happens in parallel circuit, by placing the devices in their own pathway, you reduce the total amount of resistance. And if you reduce this bottom number, resistance, and you keep the voltage the same, then as you can imagine, there's going to be more current running through the circuit. So to find equivalent resistance in parallel, okay, what we have to do here is what's known as the inverse of the resistance. So instead of adding the whole numbers up here, 10, 15, and 5, the way we're going to solve this is we're going to say 1 over R total, that's the total we want to find, R total, is going to be 1 over resistance 1 plus 1 over resistance 2 plus 1 over resistance 3. So we're working with inverses here, so that's changing the whole dynamic of the math. Sorry about that. Again, sorry about that. So this becomes 1 over, our first resistance was 10 ohms, plus 1 over 15 ohms, plus 1 over 5 ohms. So now we have 1 over our total, and if we punch this in our calculator, what we'll see here is obviously a very small number. 1 over 10 plus 1 over 15 plus 1 over 5. That's going to equal 0.367. And this is not our answer for resistance. Okay, we solved for 1 over R. To solve for our total, if you apply your algebra skills here, you want to switch spots with these two. So our total is actually the inverse of 1 over 0.367. And when we do that in the calculator, you can see that that did not work out. Okay, sorry, long pause there. That did work. So the total resistance in this circuit is 2.72 ohms. And if you compare that to the total resistance we found in series, it was 30. 30 ohms here, 2.72 ohms here. Same devices, same individual resistances, but putting them in parallel reduces the total resistance drastically. So now to find the current that is running across, we're going to use Ohm's law again. So I equals voltage divided by resistance, and that is 90 volts divided by 2.72 ohms. And our calculator here is going to give us 90 divided by 2.72, and we get 33.1 amps. So more than 10 times the amount of current that was running across a series circuit. And you can also see why, in a house, normally all your circuits are set up in parallel, so you can turn a light on or off and it won't affect the different outlets in the house. You can still use those. But if you start to plug in a large number of devices in a parallel circuit, how you can draw more current and create an overload. So that should finish up our lesson on current, electricity, and circuits. So I apologize for the long pause in there again. I really miss you guys. You guys were an awesome class. I apologize that we weren't able to build the bridges. That's always a good activity, and everybody always has fun testing their bridges at the end of the year. But it's just the way things worked out, and I know you guys will do well. And I wish all the seniors the best of luck in their future endeavors. Hopefully I'll see you guys around and we can say hi. But good luck. If you got any questions, please go ahead and post them on Google Classroom, and I will answer them as best I can. Take care.